tell that I can't multitask? I had to focus on that. Now I'm focused. So where were we? Yeah, remember the last time we've used, we found estimates for a population mean, right? The X bar, and plus or minus the margin of error. Well, now we're going to do it for proportions. So let's give you an example of what a proportion is. Can you imagine that you were interested in something like the percentage of American adults who are vegetarians? You would like to know that, right? Percentage of American adults who are vegetarians. Now, you could, I guess, ask every single one, but you know that's not the way this works. So P is the letter that represents the population parameter in this particular question. It's a population parameter, the proportion of Americans who are vegetarians. Let's just pretend for some reason Bill Gates gave me enough money and it ended up 0.12. Well, we all know that means 12%, right? Let's just say for argument's sake that's what it was. We would like to find that answer, wouldn't we? Or at least get an interval where that answer existed, right? So that's what we're after. We're going to estimate a population proportion. We're trying to estimate the proportion of Americans who are vegetarians. Now you can imagine how we're going to go about that. Aren't we going to get a sample of Americans and ask them, are you a vegetarian? And some of them are going to say yes, and probably the majority will say no. That's going to be our goal. So imagine I asked 2,000 Americans, a nice good random sample of old and young and male and female and rich and poor and usual, right? A good representation of Americans, right? And P hat is going to represent how many of them said yes. So let's say that we got right, just kind of want to work backwards here so I get some good data. So I'm going to go right, and let's say 230 of them said that they were vegetarians. Then the proportion of my sample that said they were vegetarians is 230 divided by 2,000. And that comes out at about 0.115. Now that's a bit like, you know, getting 2,000 Americans and finding out what their average age is. Isn't that just a single number, right? In this case, 11.5%. But don't we want a confidence interval? That's what we're kind of building here. Confidence intervals that estimates this number. Well, here is the formula for it. P hat. Well, that's not a surprise, you'd expect that. Plus or minus the margin of error. Wasn't it X bar plus or minus the margin of error the last time, right? So it's got the same kind of format. This is where it now changes. Suppose I wanted a 95% confidence interval. Then I do that, and then I go times. And then I would do this fella. That guy there is essentially the standard deviation. That's the sigma over root n that we got when we were doing means. Do you see it's quite different looking, isn't it? It's not a sigma over square root of n. It's got these things called p hat and 1 minus p hat. By the way, p hat is this number. Now in this textbook, you'll find that they call it p hat, q hat. P hat is this guy. Q hat is 1 minus p hat. I prefer 1 minus p hat, so I'm just going to stick to that. Well, let's see what we get then. So it's going to be p hat, which is 0.115, put it up there, plus or minus. What's the magic z-score for a 95% confidence interval? You got to hit a spacebar, maybe.
1.96.
All right. And you know you're going to write that down on a piece of paper somewhere if you can't remember it. So that's this guy times, that looks like almost everyone is here now, square root of p hat, which is 0.115, times what they call Q in the textbook, which is the same thing as 1 minus p hat. So if you take this guy away from 1, you get 0.885. And then you divide the whole thing by n, which in our case is 2000. So that's going to give me 0.115 plus or minus. This whole package here, that's the guy we call the margin of error in this situation. I hope you can see my calculator. So I'm going to go and do this calculation. 1.96 times the square root of p times 1 minus p hat divided by 2000. And the answer I got is 0.0, we'll round it off, 14. Now, if you take this number away from that guy and you take this, add this guy to him, you will get 0.101, and then you'll get 0.129. So I took this number and subtracted that decimal. I took this number and I added that decimal. And I hope, because I did it in my head, I hope that's what you got. This fella here is your 95% confidence interval for the proportion. Decimals are fine, and that's probably what you're going to have to do in your homework. To me, I just see things better when I see percentages. Now, can you see that in this particular example, we're estimating that the percentage of Americans who are vegetarians is going to be somewhere between 10.1 and 12.9. And this is based on a 95% confidence, right? So 95% of the time, we'd hopefully get an answer that was in the right range, right? And 5% of the time, you know, if we fail. Now, in my little pretend story, can you see that 12% actually works? Isn't 12% in that range? So when you create a confidence interval, you're just giving a whole range of values, one of which you hope, 95% confident, is the right answer, right? You can't say for sure that it happens to be 11.5, right? Which is what p hat is, right? What you can say a little bit more certain is it's somewhere between 10.1 and 12.9. Does that seem reasonable? It's a bit like, you know, estimating the mean, right? Somewhere between here and here, it's one of the numbers. Somewhere between here and here, it's one of those percentages, right? Okay. Now, I can add more to this. Based on this interval, why can I say with a reasonable degree of confidence that more than 10% of Americans are vegetarians? Right, that number's not a made up number. I looked at this interval before I decided what this number was going to be.
Because your lower limit is still higher than 10?
Right. Would you agree that every single one of these numbers is bigger than 10%? That's just another way of saying what Daniel just said. He's quite right what he said, right? At the other extreme, couldn't I say less than 13% of Americans are vegetarians? And wouldn't that be based on the other end? If my estimate is 10.1 to 12.9, right, can you see that there's different ways of phrasing that? Couldn't you say, I've got evidence that more than 10% of Americans are vegetarians. This interval also gives me evidence that less than 13% are vegetarians. I guess if you just use the interval, wouldn't you be saying somewhere between 10.1 and 12.9% of Americans are vegetarians? But no matter how you say it, isn't that just different ways of phrasing that information? Some people just want to know, like the bottom number. Oh, more than 10% of Americans are vegetarians. That's kind of interesting, right? Sometimes what they do is, do you know, they go back and they collect data that was like 50 years old. And they say, you know, 50 years ago, only 8% of Americans were vegetarians. And now it's at least 10%, right? It's more than 10% even. Right? There's more vegetarians in the America now. Or it could be going the other way. Maybe there used to be 20% Americans are vegetarians in, you know, the past, and now it's reduced down to 10%. But you see, you can use this information in different ways. Now, did you notice that this calculation involved a new formula, which is this fella? And this piece of the formula here, isn't that the margin of error? So you know that sometimes you're asked to calculate not just these intervals, aren't you? Very often in questions asked to write down what the margin of error would be. So far, so good? Right. So let's choose a question that is going to be very relevant, probably from now until the elections are over, where they go and ask people, who are you going to vote for, right? That kind of question. So Gallup poll have been asked in my pretend story. So they go and ask 1,024 people. And the question is, are you going to vote Democrat, right? That's the question. And when you do proportion questions, it has to be a yes-no question. You can't give them a question where they can pick A, B, or C. The math doesn't work that way, right? It's how many said yes and the rest said no, right? It's a two-way street. And it comes from the fact that this is a binomial distribution, bi meaning two, right? So bear that in mind. Let's suppose that in my story, 560 of them said that they were going to vote Democrat. And then we do 560 divided by 1,024. And the answer that I get is about 0.547. I'm just going to make things 3 decimal places. So far, so good. Now, do you know when you normally hear these on TV or you're listening to the news and they say the new Gallup poll is out, you know, who's going to win the election kind of thing? This is what they're doing. And have you noticed yet, hopefully you will after today, the next time you hear it, have you noticed that they say with a margin of error of 3%? Have you noticed they're beginning to say that? I hope, at least, you've noticed that. Pay attention the next time. We're going to get that same number. Now you're going to find out where it came from. Could be a 90, could be a 95, could be a 99. I just refuse blindly to pick 80%. You're just going to have to live with the 8% that turn up in your homework. It just cringes me to even make you think that you can do that. What do you want? You want a 99 this time? Sure, okay. So if you're going to be 99% confidence interval, that's pretty high, isn't it? So whatever we get, we're going to be pretty sure that the right answer's in that interval somewhere, at least 99% confident that it is. So here we go. P hat plus or minus the magic Z score for 99 times the square root of P hat 1 take away P hat all over n. And P hat in this case is 0.547. Has anybody got a good memory, or they just have it in front of them What's the magic number for?
2.58.
Thank you. Square root of p hat, which is 0.547, multiplied by, well, basically what's left. So that's 0.453, all divided by 1,024. So let's see what that looks like. At this point here, I think it's time for the calculator to take over. So 2.58 multiplied by a square root, that decimal, multiplied by this decimal, all divided by 1,024, and I am looking at 0.04. Actually 0.040, right, but that's fine. Now, if I convert this to percentages, it's 54.7% plus or minus a margin of error of 4%. Do you see where they got those margins of errors that you hear on the TV from? That's where it came from. It came from this calculation. So if you worked for Gallup Poll, you would just get you'd virtually get a piece of paper saying, right, the survey is over. We asked 1,024 Americans, right, a random sample of Americans, and 560 are going to be voting Democrat. At least that's what they said. And fix it. Come up with the information, right? You plug it all in here, do all this stuff, boom. Now let's see what that looks like. On this side, it's 50.7%, and on this side, it's 58.7%. Of course, when you do it in your WebAssign, right, it's decimals, but it's the same guy. So you would say latest poll, and they might even round it off. Wouldn't they say something like 54% are going to vote Democrat, margin of error 4%, right? They might do that because people don't like a lot of accuracy. I mean, we might like a lot of accuracy, but suppose someone went and did it to 6 decimal places. Oh, 54.712889% are going to vote Democrat. Do you know halfway through that they stop listening? I mean, that's what people do. So don't you want to keep it short and sweet? 54%, 55%, whatever it is, margin of error 4%. That's about as much as they'll handle that they'll want to process. Here's a question for you. If we assume that this is accurate, which it probably should be, right? 99% confident. Will the Democrats win? Is this evidence that the Democrats would win the next election? Okay, what percentage do you need to win? Let's pretend it's a two-party state, right? Forget all the other ones, right? Just two groups of people, right? Democrats, Republicans. How much of the vote do you need to win a state election or whatever else?
51.
Actually, slightly less than that. Isn't it 50% plus one person? I mean, I don't think that's ever going to happen. You never get that kind of close results, right? Sometimes you might get within a percent of each other. So you could say with a fair degree of confidence that based on this sample at least, wouldn't the Democrat win? Now, isn't there a 1% chance that it's not in this interval at all? So it could be the Republican actually wins and then everybody starts screaming blue murder about, I don't know, hanging tags or miscounted votes or whatever. Wouldn't you like to see how to do this on a calculator without all this? Now, I wanted to show you this so that you can understand that when we start hitting the buttons on the calculator, you can say, I know how to do this, but I'm only using the calculator because it's fast and easy and accurate, right? But I know how to do it. right? I know what the formula is. I know where the numbers that belong to that formula go. I know how to convert it into this interval, right? Now, provided that you're able to do that, then I don't think there's a problem on letting the calculator work. So we have to go hunting for it. Anybody any idea where it's probably hiding? Where this interval thing for proportions is hiding? What button do you think I'm going to press?
Stat.
That's a good start. Where am I going? You're correct. Where am I going next?
Over to tests.
Yeah, well done. Now, I'm going to scroll down. And it's well hidden. Do you see it's called one proportion Z interval? It's not the most, it doesn't roll off the tongue, right? But it is called one proportion Z interval. And it's choice A. So I guess you just have to remember which choice. Because I mean, there's a lot of things in that menu that kind of sort of look like the right thing, but they're not. There's only one thing that does this job, a one proportion Z interval. Well, why is it called a Z interval? Because we use Z scores in it, which is as good a reason as any, right? Okay, now I'm going to hit this guy and let's see what we get. Oh, very little that you need to tell it. They're calling the guy X. That's going to be the 560 in this case who said, yes, I'm voting a Democrat. So you type in 560. I think it's more obvious who N is. Would you agree N is kind of universal? In this case, it was 1024. I think C level, confidence level, is pretty obvious, agreed? In this case, that's going to be 0.99. This is, once you find it, isn't this probably one of the easiest menus to go through? I mean, there's not an awful lot you need to know. Once I hit calculate, boom. 0.506, well, you know, I round it off to 7, but would you agree that's the right number? Is it? There it is. And what's the other one? 586. Yeah, you see it's that guy there. 587. 50.7. 58.7. Can you see the two? Do you know you get for free the 0.547? I know it's to whatever 6 decimal places, but isn't that the same number rounded off? So one proportion Z interval. And it's option A, and you get it from stat test. I mean, that's a bit cryptic, but wouldn't that be enough to figure it? Hit stat, go to test, pick option A, and you're there, right? So far, so good. Right, let's do another one proportion Z test, and this time I'll use you lot. How many we got? 1, 2, 3, 5, 10, 15, 20. There's somebody missing. 5, 10, 15, 20. Oh, they must have left. We have 23 people. I'm going to do a 90% confidence interval because I've just decided to do that. And I'm going to ask you a question and you stick your hand up and we're going to use you lot as our sample. Not a big sample, but it's the best I've got. And we are going to ask you, do you have a pet? So stick a little hand up or indicate it in some way and we'll count you. So on the top row, 1, 2, me 3, 4, 5, hand up 6, hand up 7. Anybody else? 7 gets the job then. Cool. Now, 7 out of 25. Why did I say 25? 7 out of 23. Maybe I was hoping it was 25. 7 divided by 23, we get the answer 0.304. I'm going to stick to 3 decimal places throughout this. Now we're going to do the calculator version, aren't we? Much easier, quicker. So I'll clear that one out. I'm going to hit start. I'm going to move over to tests, and I'm going to scroll down to option A, one proportion, type it in this case 7 of you out of 23, using a 90% confidence interval, and go. That's how quick it was, wasn't it? And we get, as our interval, 0.304, oops, scanned the wrong place, 0.147, and then in the other side, 0.462. So that's somewhere between 14.7%, and it could be as high as 46, that's horrible, 46.2%. Why is that interval so huge? Because the last one was give or take, 3 or 4%. Why is that one all over the place?
Is it the sample size?
Yeah, it's horribly small, isn't it? Horribly small. But, I only have 20 odd people in the class. So I guess anytime I do something, we're going to have to suffer that consequence. So that's our guy. Now, here's something we don't know. Very often they ask you to write down the small answer and the big answer. That you can get. But they also want you to very often do the margin of error. Now, I can find the margin of error using this interval. I don't have to recalculate it, right? I don't have to just go back and do this kind of thing, because that would take forever, right? Any ideas how we use these limits, the outer and inner limits here, to come up with the margin of error?
Subtract them and divide them by 2.
Yeah, exactly. Is it not the same thing that happened? Hopefully I mentioned that. Is it not the same thing that happened when you wanted to find the margin of error when you were using the mean? Big guy take away little guy, halved. Okay, let's see what that looks like then. If you go 0.462 and you subtract 0.147, you get that, and then you divide it by 2, and the margin of error is 0. I'm just going to call it 16 because I don't want to write all those guys down. So our answer to what percentage of Americans have pets, it would be something like 14.7% up to 46.2%. Or you could write it down as 34% plus or minus a margin of error of 16%. I mean, that is equivalent to that. Can you see I already know p hat, and I've just found at least a rounded off version of the margin of error. And so a margin of error of 16% is huge, right? Because there's lots and lots of places where that would happen. But I could say some things for sure. If we call the majority of Americans 50% or more, wouldn't we say that the majority of Americans don't own a pet, don't have a pet? You agree? None of these numbers are 50 or beyond. So I could say that. So you might get a question saying, is there enough evidence to show that the majority of Americans own pets? And the answer is no, there's not. Now, I'm going to do a cheat here. Can we pretend that n was 230? And just by sheer good luck or fortune, the exact proportion-wise, the exact same number of people said they had a pet. So essentially, the only thing I'm doing with this question is I'm increasing the size of the sample. What do you think is going to happen to this margin of error if I now increase the sample from 23 to 230? What do you think is going to happen to this margin of error?
It'll decrease.
It certainly should. Well, I'll stick this in the calculator and we'll find out. Clear this out of the way. Start, over to tests, down to A. This time we're going to say 70 people out of 230. I'm going to keep everything else the same. And the interval has changed quite a bit. The interval is now, I guess I put it over there, you can see it while I'm writing it. 0, I'll turn it into percentages, that way we're comparing like with like. It's 25.4% up to 35.4%. And the margin of error this time is now 5% compared to 16. Do you see it's a vastly improved estimate, isn't it? Would you agree these numbers are at least closer? And would you agree definitely the margin of error right is 3 times better? Now I'm not going to do the next one. Suppose I made the sample 2,300, but I kept, you know, the proportion the same, right? Wouldn't you expect an even smaller margin of error? And if you did 23,000, you could probably nail the percentage of Americans that own a pet with a sample size of 23,000 to give or take, you know, 0.1%, right? That's how good it would be. And that's phenomenally important, because doesn't it mean we can get really accurate data without having to ask 300 million Americans, 300 million plus Americans, anything? Can't we get by with just maybe asking 1,000 or 5,000? As long as it's a good sample, we'll get good data. Agreed? Now, one last example of this, and then I'll talk about how you can judge how big a sample needs to be to get the accuracy, the margin of error that you're after, right? And that's coming after this. So for our last question, I hope I can make this data work. There's another election coming up. In this election, let's say it's the governor of Texas election, right? And so they collected a sample of 500 people, and they found out that 508 of them, not 508, sorry, 258 of them, that's better. Do you know, if 508 people in Texas and there's only 500 to choose from, that would get me a little bit suspicious. It's a bit like, I think you have some people who come out and they tell you things, especially at the elections. Don't you collect data in counties? Is it called counties? And they come up with data that there are more people voted in Clark County in Texas, wherever it is, than there are people in Clark County. And nobody seems to be too surprised by that. Oh, come on, isn't there always at least one story kind of like the one I just mentioned? I made up that name, but that's what happened. So you should get a little bit concerned if something like that happens, but in general, things are fine. Okay, so let's see what that guy looks like. 258 divided by 500. It's 0.516. So that's 51.6%, right? That's who's going to vote for the Republican governor of Texas. Based on that one number, does it look like the Republicans might win Texas as far as governors? Yeah. Let's do an interval and find out if it's as sure now. Because one number doesn't really give you the big picture. I think an interval gives you the big picture. So, got my data already set up. Let's do, I don't know, let's do a 90% confidence interval, just because I can. So, start, move over to tests, move down to 0, A, gotcha, there we are. Type in 258 out of a sample size of 500. Oh, we'll keep that confidence level. Enter, and now we have 0.479 up to 55, 0.553, which I would call 47.9% up to 55.3%. Now, back to the same question. Are you sure, as you were a little while ago, that the Republicans are going to win Texas? Would you agree this interval contains situations like this, where he will or she will? But couldn't it be numbers like 47 and 48? Now, we'll assume it's a two-horse race, right? So if 48% vote Republican, doesn't that mean 52 voted Democrat? Now, I know your political system is sometimes a little bit awkward. Do you call them spoilers? Or where you have a third or maybe even a fourth candidate for the governing the election? And the reason I think they call them spoilers is, don't they take, very often at least, don't they take votes away from one of the two guys? So what the Republican wants is a Democrat and somebody like the Green Party. Because wouldn't the Green Party probably suck mostly Democrat votes away? Right? And the Democrat would probably want a Republican, right? Because he knows he's going to get that. But wouldn't they want something like a Tea Party candidate, right? An independent Tea Party candidate? Because wouldn't they probably suck away some Republican votes? And because of that, can't you actually win an election with less than 50% of the vote? You just need a big enough spoiler candidate, don't you? If I was Machiavellian, which I probably am, wouldn't it be a really good idea to help a spoiler candidate if they were going to take votes away from the opposition? Can you imagine that kind of, get a donor that doesn't even like the Tea Party, right? To encourage the guy to vote, right? To go out there and take votes away. Or a libertarian candidate, or a Green Party, right? I wonder if that's ever happened. Do you think it's ever happened that the opposition have encouraged a spoiler? I don't think it's illegal, is it? Just curious. We don't have as much fun in British politics. Our politics are so boring, you'd fall asleep watching them. But you lot have such, what's the word? Interesting politics. Right? Yeah. Anyway, one last thing, and we're finished with this section, which is probably a good place to be. It's an interesting question. So here it goes. Suppose I want a margin of error of 1%. So basically, I want E, because everything works in decimals, right? I want E to be 0.01. With, let's say, a 90% confidence interval. Here's the question now. How big should my sample N be? So if you want to make sure that your margin of error is give or take 1%, how many people do you need to ask to make sure that that's going to be the result, right? Now you can imagine you could ask 1 million people, but wouldn't that be overkill and you probably get more margin of error than you want, right? And you could ask 50 people, but that probably wouldn't be even close to what you want. So there's some middle number, right? There's some perfect number out there that's just going to get you this 1%, right? That guy and nothing else. Can you remember what the formula looked like when it was doing how big the sample should be if it was a mean that you were after, right? And you wanted a particular margin of error E. There's a start for you. Can you remember anything else? Nope. You would go Z.9 sigma, right, over E. So if I wanted to get, you know, a margin of error or whatever it was, you put that number there. Z.9 is the classic magic number, in this case 1.65, and isn't sigma known, and you go and look up the question because they told you it was 5 or 14 or whatever. So wouldn't it be nice if there was a formula that done this job? And here it is. So you just have to write this guy down somewhere, and hopefully now the formula has a little bit of an issue here. You're going to find how many people to ask before you know what p hat is, right? Technically it's p, but in real life it's really p hat, right? So how do you get around that? There are two versions of this. If you know nothing, right, you have no idea what kind of answers you're going to get, right? You could get a huge number of people, you could get almost nobody, right? If you know nothing, you make p hat a half. And so this formula will now become 0.25, this guy over E squared. So if you don't know anything about the question you're about to ask, right, you have no clues at all, which is probably the most likely thing, you basically pick a number in the middle. Would you agree 0.5 is in the middle? It's not hugely big, it's not hugely small, right? It's not 0.1, it's not 0.99. In the middle, call it 0.5. And if you make this guy 0.5 and you make this guy 0.5, do you see where this is coming from? 0.5 times 0.5 is 0.25. Well, let's do that one. So 0.25, and the magic number for 90% is 645. The margin of error that I had in this question over here is that guy squared. Let's see what we get then. 0.25 multiplied by a bracket. Oh, let's try that again when you can see it. 0.25 multiplied a bracket 1.645 divided by the margin of error squared. And the answer, whoa, you will need to ask 6,766 people. Now, if you look really carefully at my answer, You might think the answer should be 6,765, but don't you always round up to be safe? Even when the rounding up is a 0.06, it still counts as a person, right? So if you want a 1% margin of error, do you know that you have to ask probably somewhere in the region 67,000 people, right? The typical Gallup poll one, and if you get into it, you'll find it's very common with all the others, like Quinnipiac and so on, is about 1,000 people. So this is like 6 times bigger, 6 times more expensive than the typical poll that you'll get when you read a newspaper article or you see a newspaper, say, you know, a TV show saying latest poll, right? They're probably only going to be doing roughly the margin of error is somewhere around about 2-3%. That's the going rate for, and that's what you get when you take about 1,000 people. So see, for 6,000 people, you know, you probably are only going to half the margin of error. There's a kind of law of diminishing returns. To get a really small margin of error costs a lot more money than you think it should cost you, right? You have to ask 6 times as many people just to get a 2% down to a 1%, right? Seems a little bit unfair, but that's how it works. Try another one. Now I said there's 2 versions. So here's the second one. If you know that p hat is probably, I'll pick a number, 30%. Now how you would know that, I haven't a clue, but let's say you did, right? The number is now going to be p hat 0.3, 1 minus p hat 0.7 times this mess, 1.645 over 0.01 squared. See what that looks like then. 0.3 times 0.7 times a bracket 1.645 divided by a margin of error, and then you square the whole thing. And now it becomes only 5,683 people. Well, it's about 1,000 less, isn't it? Now that's based on very shaky ground. How do I know that the answer is going to be somewhere around about 30%? I'm not sure how you could even ever do that, unless you've done lots and lots of samples of the same kind of people, you know, in the past. Like you've asked Democrats last week and you ask Republicans next week, and you've got a kind of working value that they're not going to change much. Right, the last time I done it, it was 30%, so it's probably going to be about 30% this time. I guess you could argue that. And you plug that in, right? That's the sample size, and off you go. And according to the formula, at least, that will guarantee you at the 90% confidence interval level a margin of error of 1%. It's not the fact that that number's 0.3 that makes this smaller. Do you know if this number was 0.4 or 0.2, it would still be smaller? And it's a bit like, if you know some information, doesn't that mean you need less people to be accurate? That's kind of what this is reflecting. I could have made that 0.12 or 0.87, and it would be slightly different each time, but it would always be less than that. So when you pick this magic 0.5, it's not just a guess, it's like the worst case scenario guess. Everybody's going to be at least better than that, probably. So that might be slightly overkill, and that's why it works so well. Any questions before we go looking at what the homework questions look like? Are we good so far? Right. I think that went pretty well. I saw a lot of nods. Nods are good, right? I didn't see too many deer in the headlight looks, which worry me when it happened. Let's see if we can find that darn guy. Here we are. Okay, let's look at a question. there's going to be a story at the top, and then they go through a whole load of stuff down here. Maybe I should just do this one. I've got my calculator handy, so I should be able to fill it in for you. Carry at least, yikes, 4 decimal places. Okay. I promised to do the question. I shall do that. Answers may vary slightly due to rounding. Oh, good. So if I kind of round off a little bit more, I'll be safe. In a random sample of 62 professional actors, it was found that 42 were extroverts. That's surprisingly small. I would think to be an actor, you would probably need to be an extrovert, but what do I know? Right. So P hat, won't that be 42 divided by 62? Right, that's P hat. So on my calculator, I'm going 42 divided by 60, I've lost the number here, 62. And I have got the answer 0.6774, sticking to their 4 decimal place rule that they wanted. Now, I know they call it Q hat, but isn't Q hat what I call 1 minus P hat? Right, so that's just a name. So if you take that guy and you want to get him, don't you basically subtract the first guy from 1? So what do I get? 0.3226. Yeah, okay, that's cool. Find a 95% confidence interval for P. And then margin of error is going to go here, lower limit's going to go here, upper limit's going to go here. Although you can't see what I'm doing, can you just trust me? I'm going to be doing it in the calculator and we'll see what it looks like. Okay, so I'm hitting start, I'm going over to tests, I'm going down to our guy A, I'm hitting it as we speak, and I'm typing in 42 out of 62, and I'm doing a 95%. And then I'm hitting calculate. And the answer that I'm looking for the small number is 0.5611. And then for the upper limit, it's going to be 0.7938. That seem good? Now, there's a guy that I kind of skipped. Let's figure him out. Do you know when you do the calculator, it doesn't tell you E? Don't we have to do that little workaround? And just to remind you, don't you subtract these two and divide them by 2? That gets you the margin of error. So that's what I'm doing right now. I'm typing in 0.7938, and I'm going to subtract 0.5611, and then I'm dividing that by 2, and I'm getting to the 4 decimal places, 0.1164. The way my brain would work is somewhere in the region 56 to 79% of actors are extroverts. That is 67.7% with a margin of error of about 11.64%. That probably tells you everything you need to know now, doesn't it? You got a kind of ballpark figure for what percentage of actors are actually extrovert. And then we got a couple, they like to chuck a couple of multiple choice things here. Give a brief interpretation of the meaning of a confidence interval. By the way, this was a 95% confidence interval, right? So we are 5% confident that the two, no, I don't care about the 5%, so would you agree it's something to do with 95%? We are 95% confident that the true proportion of actors who are extroverts fall outside that interval. Now that's the back to front, isn't it? Would you agree it's the last one? We are 95% confident that the true proportion of actors who are extroverts fall within this interval. In other words, they're inside that interval. Cool? And do you, oh, darn it. I didn't mention, because I'm forgetful, the conditions that you're allowed to use this process on. They're pretty straightforward. they're not mentioned on all of them here, but would you agree that some of the conditions are things that we just take for granted? Shouldn't it be a simple random sample? It shouldn't be some weird sample where you only ask guys, right? Shouldn't the sample be large enough? And shouldn't the question be asked in an unbiased way? So don't say things like, if the election was tomorrow, would you vote for those horrible, evil Republicans? Or if the election was tomorrow, would you vote for the really communist Democrats, right? Or whatever insult you can come up with, right? That's definitely a bad idea, right? So we'll assume that. This weird thing up here is not standard, but then again, this book seems to have its own little quirks. Do you see how it's saying NP has to be bigger than 5 and NQ has to be bigger than 5? You take your sample size, which is N, and you multiply it by this guy, and it has to be bigger than 5. Technically speaking, it should be bigger than 10, but I'm going to just call it bigger than 5 because that's what you have to deal with here. There's an easier way to interpret this calculation. At least 5 people have to have said yes, and at least 5 people have to have said no. That's what it boils down to. NP is the total number of people who said yes, and it has to be at least 5 people. And NQ, right, that's the 1 minus P guys, they're the people who said no, and that has to be at least 5. So when does that crop in? That typically doesn't really matter because almost every sample you could ever think of, that's going to be true. Can you imagine almost any question you ask? As long as N's big enough, aren't you going to at least 5 people are going to say yes? At least 5. And there are probably at least 5 going to say no. But there can be exceptions. Suppose you were looking for a very rare event, like God, I should try to think of something that's really rare. Suppose you asked a group of 100 people, do you think politicians never lie? Could you imagine you might not get 5 people to say yes to that question? I guess that's a double negative. 5 would say yes or 5 wouldn't say no. Can you imagine that might well be a very, very small number? That would be the only example that I can come up with in my head where things fall. So here the conditions are at work. So you pick the one that says yes, because in this question here, didn't 42 of them say, yeah, I'm an extrovert, but didn't the other 20 then say, no, I'm not an extrovert? Would you agree you get more than 5 in both cases? I know you have to do it for this book, but will you please try in real life, if you have to do it out of this class, change that number to 10. And at the same time, will you please never, ever, ever do an 80% confidence interval? You will get laughed out of. If you tried that in university and you're doing a postgrad and you do a report and you use an 80% confidence interval, your professor is going to have a really interesting conversation about who did you get for statistics, because I'm going to complain to the college. So I've covered my butt here, right? 90, 95, 99, everybody pretty much except the guy that's written this book uses those numbers, right? That's the only real ones in town. In that same vein, will you remember NP and NQ have to be bigger than 10, because that's really much more standardized. Are we comfortable about this process? Right? If you go through the questions, they just keep changing the story, but the process isn't going to change. Here's one about judges. Evidently, they like extrovert and introvert. Can you imagine that P hat's going to be 281 out of 512? Can you imagine that these questions here are pretty much the same kind of questions that all the other ones ask? So you're going to continually saying the 4th one, the 3rd one, or something like that. This one's a little bit better. At least they ask you a margin of error, right? So occasionally you're going to have to find it. Pretty standard. I haven't even looked at the story yet. Santa Fe black on white is a type of pottery commonly found at archaeological excavations. Where is she? Olivia, you with us? I lost her. Okay, she would probably tell us about that. I think I know what that is. Isn't that just a native pottery where there's a lot of black and white in it? I'm assuming. It's got the little zigzag things on it. Am I the only one who knows what that is? You're just going to, I could say anything. It could have happy faces. You didn't know that the Native Americans used to play little black happy faces on their pottery and little white eyes, and that became the Santa Fe black on white. None of you believe that story, I hope. Right? Moral of that story is don't believe everything your professor tells you, right? Including me, right? Except the 80% and the 10, right? Believe those two things, right? Everything else, be critical. Big samples, big story. Huge sample. Oh, okay. Oh, okay. This is, I guess, interesting. I wish they told me what year it was. Or maybe that's a grand total. Maybe that's a running total. You know, 10,426 convicts have escaped from certain prisons. Only 7,488 were recaptured. So I guess you might call that the success rate of prison breaks. So that means there's 3,000 of them roaming about right now. That's not good. Yeah. My wife loves watching criminal programs, you know, true crime. And I solve them really quickly. Somebody gets murdered, because that's what happens. And I say to my wife, it was the husband, the boyfriend, and it was for insurance money. And do you know how many times I'm right? So I've got a cure for that. I used to have a cure for that. I had very little life insurance. So there is no need for my wife to kill me for that. But unfortunately, I got sensible and I actually have quite a lot of life insurance now. But if I ever die mysteriously, will you remember this conversation? And if my wife starts telling me that skydiving is really a good sport, that's probably another clue. Okay, so I'm just scanning through these. I don't think there's a lot of difference between them all. Would you agree? There's probably some stories at the end. And the only one I can find that uses the guy that we're talking about is this one here is to do with how big the sample should be, right? So it's the last question in the batch. Everyone after that, let me redo that. The last two questions in the batch, right, are finding the thing. So in the first one, you're going to use 0.5, right? Because they tell you to. Oh no, sorry, the margin of error is that guy. But you're going to use 0.5 because you don't know anything. And in this second one here, aren't you going to use a p-hat of 0.6? Still looking for a margin of error of 0.5. Do you want me to do that last one, or you feel you can figure that out yourself? You want me to do the last one? Okay, so I'm just going to write the numbers down here. They want me to get a margin of error of 0.05, which is essentially 5%. And in question A, I don't know anything, which means I'm going to use p-hat of 0.5. And in question B, for some reason, I know that p-hat is 0.6. How do I know that? Because you see down here, they've said it indicates that it's probably going to be about 60%. So let me leave that guy. And here it goes. Ah, darn it, excuse me. I was just getting my formula, make sure I didn't screw up. Oh, darn it in space. Can anybody remember what confidence interval that question was? Because I need to know that. If not, I'm just going to pretend it's 90% and you can tweak it later. Does anybody recollect what confidence
It's
interval?
99.
99. Yep.
Well done, thank you. So it's going to be a 99 over a margin of error, right, squared, right? So that's just something you write down and remember, and you bring it up when you need it. Now, in the first question, since you don't know anything about the question that you're asking, right, as a total guess what P is going to be, you use the 0.5, 0.5. This guy here is 2.58. This guy here is that number. And then you square it. So on my calculator then, 0.5 times 0.5. That's where that 0.25 that I gave you came from. Then I'm going to multiply that by a bracket, and inside the bracket 2.58. I'm going to divide it by 0.05, close the brackets, and then square it. I can find the square one there. And the answer that we get is 666 people. So if you want a margin of error of essentially give or take 5%, do you know that you need about 666 people? Okay. Now the second question went and said, we believe the answer is probably 60%, right? Somewhere there. So our formula just adapts a little bit. And p hat now is going to be 0.6. 1 minus p hat is going to be 0.4, and this stuff here is going to be exactly the same. So it's going to be about 2.58 over 0.05, and then we're going to square it. So I'm going to go in here, clear this one out of the way. 0.6 times 0.4 times a bracket, 2.58 divided by 0.05, and then square the little guy. And 600, oh, would you look at that? Don't I still have to call that 640? Agreed? Even a tiny bit out, you still round up. So if you know nothing, you need to get 666 people to make sure the margin of error is 5% or less. If you know a little bit about it and you're comfortable that it's true, do you see that you now need only 640 people? They're not a heck of a lot difference, would you agree? If you were a little bit worried, do you know you might just say 700 because it's a nice round number? And won't 700 guarantee not just 5%, but probably even better than 5%, right? A margin of error of 4.5% or something. Is there any questions, or are we good? We're good? Right, so I'm going to give you a 10-minute break. I'll go and give my dogs a poo walk because she's at the back there doing her thing. And then when you come back, we'll be looking at our last section, which is a little bit longer than this one. But yeah, we'll wait and see what it's about. Okay. Last section, as I promised or threatened, I'm not sure which way, 7.4 is going to be fairly long. There's a lot of things in this one section they could easily have broken into two. In fact, I think they should have, but I'm not in charge of the book. The first section would be these two guys. We're going to now look at estimating the difference between two means. One when you know the sigmas and the other when you don't. So it's a kind of extension of, remember we did estimate of a single mean when you knew sigma, and the estimate of a single mean when you didn't know sigma. Remember we did those kind of questions. Now we're going to look at two. So that's what that is. And then the other one I think would have been better in its own section is we're going to look at estimating the difference in proportions between two groups. So I'll give you a kind of context of this. I'm going to call them A and B.
We can't see it.
You can't. Have you noticed I am really good at not swearing? Come on, I've had plenty of things that happened that would get, darn it, you've gone. I've lost you. Right. It's kind of about my day today. This was a good example of what I'm talking about. I've lost you again. What the heck is going on?
We're still here.
Yeah, but my white screen isn't, and I'm having issues finding it. Where the heck are you hiding? Normally when I close everything off, there's a little tab and I hit on it and it does it. I'm kind of, no. Oh dear. You can see me, but not the white screen. Is that correct? Right, I am going to see if I can find what happened to that window that I need to do my thing. Oh, that's not good. This hasn't ever happened before, so I don't know how to fix it. I should have along the bottom a little thing that I hit and I get all my windows back. I think it's here. I just have to make it happen. Come on.
Do you have a Mac or a PC?
I have a PC.
You could, with my PC, I swipe up 4 fingers on the mouse pad thing.
Yeah,
And I
mine's
get
is a
all the
PC with a
screens.
mouse. Yeah. Yeah,
You
mine's
have
is
a
just a
button.
PC with a mouse, darn it. Okay, let me think. How am I going to do this? I may have to leave and come back in. It will only take more than a couple of minutes, so hang around. I think that might be the easiest way for me to do it, as long as I don't cancel the Zoom meeting by accident. So hang about. If by chance I screw up and I cancel the meeting, I will recreate a brand new one and send it to you. You can join us. The worst case scenario, it'll be 10 minutes between the start and the finish. So here goes. I can leave meeting, that's good. And I'm going to, it looks like I have to assign it. So who's getting the job? Courtney, you've just been given the job of being in charge of this while I leave. Whoa, that was dangerous. I have no idea what I did, but I don't want to do it again. So here we go. Right, are we good now? We're back to whiteboard, and whatever it is I screwed up, I hope I don't ever hit that button again, whatever it was. Okay, so what we're going to have here are 2 groups, A and B. These are going to be 2 separate populations. So can you imagine population A was male Oh, let's do different animal. Male tigers. And population B is going to be female tigers. And we take a sample of 200 male tigers, which I'm going to call N1, and the mean weight of them was 280 pounds, because I'm just making this up, right? And then you took another sample, a different sample, and it was only female tigers, and you found 150 of those, and you weighed the female tigers, and they came out as 260. So far, so good. Let's suppose that for some reason or other, because I've done this job for a long time, that I know the standard deviation of male tigers is 10, and that for female tigers it's 5. What we're going to do here is we're going to estimate the difference between them. So if we're talking about a mean, won't it be called mu1 for this guy, and we'll call this one mu2? So we're going to essentially estimate the difference between the two. So I'm not going to estimate what this is. I'm not going to make an interval estimate of this. I'm going to make an interval estimate of the difference between them. And that way we can kind of compare the two to see if there's any differences at all. Now, there is a formula. It is really ugly formula. I'm going to show you it twice, and then I'm going to show you how you do it in the calculator from that point onwards. So the formula for estimating is this guy, plus or minus the margin of error. The formula for getting the margin of error, however, is a little bit nice and then very ugly. Can we suppose here that we wanted a 95% confidence interval, just for argument's sake, right? Then this guy here is the magic number for a 95% confidence interval, right? That's cool. And then you finish with a big ugly square root. And it's sigma 1 squared over n1 plus sigma 2 squared over n2. You agree that is just one ugly looking formula. And it is what it is. If you want to get some kind of justification of where that came from, see if I cover up this bit and you look at just sigma 1 squared over n1, see if you simplify that, do you know you just get sigma over root n? And remember, that's what the formula was when it was one guy. So this is what you do when you have to combine two guys. So in this particular story, 280 was the male average, a little bit less was the females. A 95%er is 1.96, followed by a square root of 10 squared divided by 200 plus 5 squared divided by 150. Would you agree it's kind of plug and chug, right? Everything's got a place and you put the number in where it belongs. Now this chunk here that I'm scanning from here to here, right, that's going to be my margin of error. And would you agree these two guys just come out to be 20, right? The difference is 20. Right, I'm going to try my best to do this calculation on this fella here. And so it's going to be 1.96 times a square root of 10 squared divided by 200 plus 5 squared divided by 150. And the answer I get is, oh, it's an interesting answer, is about 1.6. So our estimate for the difference in weights between male and female tigers is 20 pounds with a margin of error of give or take 1.6. That would end up coming out to be what, about 18.4, and it could be as large as 21.6. So the difference in weight between male and female tigers is somewhere in that range. It's a difference in weight, average weight, right? Because you know you're going to get some skinny male ones and big fat female ones, right? And vice versa, right? But this is an average of the males compared to the average of the females. Now, mu1 take away mu2, right? That's what we're estimating. Do you notice that these numbers are all positive? Great. That means that the difference is positive. Now, with a little bit of math, if the difference is positive, isn't that true? If mu1 take away mu2 is greater than 0, if you add mu2 to both sides, isn't mu1 bigger than mu2? What that tells me is that this interval has got quite strong evidence. We have evidence. I would probably stick in the word strong, but that's, I guess, a matter of opinion. We have strong evidence that male tigers weigh more, on average, than female tigers. Now, do you see how I came out with that conclusion? If the difference is positive, doesn't that mean the first guy has to be bigger than the second guy because the difference is positive? Do you know you could get an interval where they're both negative? A different story. If they were both negative, wouldn't that mean the first thing is typically smaller than the second thing? That's why you get a negative answer. And wouldn't that be evidence then that the first thing is typically, on average, less than the second thing? I can say even more about this particular one. Not only can I say with a fair degree of confidence, a 95% confidence, if you want a number on it, that male tigers are heavier than females, but can I also say that they're probably, on average, 18 pounds heavier than females? Because isn't even at the small end, isn't 18 the worst case scenario for the difference? So way more than, I'd probably put it there, weigh 18 pounds more on average than female tigers. So it allows us to estimate the difference between two different groups, two different populations. And it's a pretty messy formula, but it does its job. And now I know that the difference is somewhere in that range, which means that I know that the first group is bigger than the second because everything is positive. We comfortable with that process? It's a little bit ugly, and certainly it's time consuming. So I said I'd do two. So here's my second story. Let's suppose that we had A is Scottish people and B is American. And I took a sample, I'll call it N1, of 250 Scottish people. And the average height was 65 inches. And I took a sample of 300 Americans, and I found out that the average height I got out of them was 67 inches. And for some reason or other, I know that the standard deviation of Scottish people is 20. That's a bad number. 2, that's better. And for this, the Americans, it's 3 inches, right? And we are going to find a 99% confidence interval of the difference between them. So this is going to be the second and last time you're going to see that ugly formula. After that, we're going to just do the calculator version. So, x1 bar, take away x2 bar, plus or minus the magic z-score for 99 times this ugly guy. Sigma 1 squared over n1, sigma 2 squared over n2. The numbers are 250, take away That's me and my scanning. 65, take away 67, plus or minus 2.58, square root of 2 squared over 250 plus 3 squared over 300. Now, when you subtract these two, do you see you get a negative number? It's -2. And this mess here is our margin of error. So here goes. 2.58 times the square root of 2 squared, I'll do that in my head, 4 divided by 250 plus, I can do this in my head, 9 divided by 300. And I am looking at a margin of error of about 0.55. Now that comes out to be negative 1.45. Right, start again. That comes out as negative 2.55. And then on the other side, it's negative 1.45. So the difference between heights of Scottish and Americans, right, the difference between them is this. Do you notice that these are all negatives? Right? Every single difference is a negative number. Now, if it's negative, doesn't that mean that this guy is negative, right? Less than 0. And that means that. So doesn't this mean that there's strong evidence that Scottish people are less tall than Americans? That makes sense? And if I was going to put a number on it, wouldn't you say about almost 1.5 inches smaller, 1.45? Are we okay with what we just did there? Yeah, okay, I like that. Now I am going to show you that same calculation on this fella. Okay, so we are going to look for an interval that tells me the difference in two means, right? Between two means. Anybody want to have a guess where I'm going to find this guy? Correct. Where am I going to go after stats? Correct. I've seen your lips move. Now, I am scrolling down here, and I am going to keep scrolling because the guy that we want is there. Now, when I hit enter, I move over to stats and I hit enter. Now, this question was based on information where all we gave you were the statistics, right? I didn't give you the raw data. I just told you what the mean was and whatever else. Right. So that's why I'm using the start menu. Now, as we scroll through it, this has just got old data. Sigma 1 is 2, which is cool. Sigma 2 is 3. X1 bar, oops. Is 65. N1 is 250. You all happy about where I'm getting these numbers? They're coming from over here. Right, if I get a little bit distracted there. If you do X2, it's what, 67? And N2 is 300. And the confidence level that I'm looking for was 99 in this case, wasn't it? And now I'm going to hit calculate in a few seconds. Barring some rounding off, shouldn't my interval look like this guy? Right, it's the same question. Does that look like negative 2.55 and negative 1.45 barring some rounding off? You see the negative 2.55 matches the first number, and negative 1.45 matches the second. Have I convinced you that the hand method and the calculator method are doing the same job? But isn't this making your life 10 times easier? Because all you really need to do is put in the information, right, as it happens, right? So far, so good. Now, since I want to do as many of the questions that are coming later using this method, right, using the calculator, let's show you another longer version of this question. Suppose you have A and B, and A is going to be how long it takes you, because I'm going to be sexist today, how long it takes you to get ready in the morning. And A is going to be people who self-identify as male, and B is going to be those who self-identify as female. And we got some samples, and it took 15, 3, 12, 8, and 10 minutes for this very small sample of 5 people. And it took 22, 17, 23, 25, and 11 minutes for this sample of 5. Now, they don't need to be equal, I'm just making them equal. Superficially, does it look like females take longer to get ready in the morning than males? Because I'm being sexist. Right? Let's find an estimate for the interval of their differences and see what that looks like. Now I'm going to hit start again. I'm going over to cat tests, and I'm going to scroll down to 2 sample Z interval, right? The same place we were a few moments ago. Number 9, 2 sample Z interval. Now I'm going to hit enter. And then I'm going to go over to data, and I've just realized something. Didn't I forget to put the data into my calculator? I did this earlier today. So I'm going to hit start. I'm going to hit number 1 edit, and I'm going to put my data in a few moments. So here we go. For the guys, it's going to be 15, 3, 12, 8, and 10. And on the second column, I'm going to put the female data. So 22, and 17, and 23, and 25, and finally 11. Right, now I'll go back and do what I just did a few moments ago, but now it'll make sense because I have the data waiting for me. I'm going to scroll down. Oh, can you remember what number it is? Which menu choice am I going to use to get the difference here?
9.
Right, okay. Do you see it? 2 sample Z interval. I guess you better write little notes to yourself where to find all these various menus. Have you noticed that we're beginning to get a lot of them? And you might get confused about which menu, which menu choice for which situation, right? So when I hit this fella, I'm going to choose the data choice here, right? And would you agree that, well, I'll have to tell you here. Can we pretend that somehow I know sigma, because you need it for this question? And somehow I know that sigma 1 was 5 and that sigma 2 was 6, just for argument's sake, right? That'll be part of the question. So suppose you were told that this was 5, right? And you were told in the question, this is 6, right? Because sigma is known. Right, now I can continue. And would you agree L1, L2, leave it alone? And I wanted, I don't know, did I mention what kind of confidence interval I wanted? No? Okay, give me one. What should I go looking for? What kind of confidence interval do you want?
90.
Okay, so we're going to find a 90% confidence interval because we need to know that, and that's given to you in the question, right? And so about to hit calculate. Since these are smaller than that, it wouldn't be a surprise that the interval contains either mostly negative numbers or all negative numbers. Let's see if that's true. negative 15.75 to negative 4.255, right? So the estimated difference between times to get ready in the morning between males and females are these negative numbers. What's that evidence of? Do males take longer or less time to get ready? Less time, yes. That's what Kerry's mouse was saying, less. Great. If these are all negative, what you're saying is the first population mean, take away the second population mean, is negative. Now, is it negative in mathematics means less than 0? And then if you add this fella to both sides, it's a little bit of algebra, but not much. Can you see why negative intervals mean the first guy is smaller than the second? What does a positive interval mean? Right, where all the numbers inside are positive. If negative means the first guy is less than the second, what do you think a positive interval means? You probably should hit the spacebar, because I see your mouse moving, so I'm pretty sure you were saying it. Would you agree that's evidence that it's the other way around? So you could go to a magazine and get into real big trouble and say, it's now been scientifically proven that females take longer in the morning to get ready than males. And people will accuse you of being a really horrible sexist person. And since I made up these numbers, I think that would be a valid argument. But can we pretend for a minute it was true? Is something sexist if it's true?
I mean, I don't think anyone is going to argue with this on this fact. It's
Well, I mean, I could, make up another one. In general, if something is true, does that make it sexist? Whatever that thing is.
I think if it's something innocuous like this, I don't think it is. It just is.
It is what it is. Right. You could argue that it's a positive thing. Little boys are not very good at being clean, and probably little girls are better at being clean. So couldn't this be a reflection of how clean each group is? So it's not necessarily a negative thing, agreed? Not necessarily, at least. Okay, so as far as I'm concerned, are we happy about how you answer questions about finding an interval that measures the difference in means when sigma is known? Right, that's what we've just spent a fair chunk of time doing, right? So we're now going to move on to how do you find difference in means when sigma is unknown? Which really is realistic. I mean, it's very rare that you would know sigma. It just is. So far so good. So let's do another example. Let's suppose we have two groups again. This group is going to be Alaska, and this group here is going to be Washington. And we collected some data, and this time we collected data on what? Try to think something pretty innocuous. On how much rain falls in July, right? How many inches of rain on average? Now you can imagine Alaska, some places might get 2 inches of rain in July, other places get 5 inches and so on. So we're averaging it out. So in Alaska, they found 100 different locations, and in July they counted how much rain they got, and the average amount of rain that they got, according to my made-up story, was 15 inches. And the standard deviation of my sample, now remember that's based on the data, right? So I'm telling you up front, right, the standard deviation was 3 inches. I'm not telling you sigma, right? I'm telling you a number that you could calculate. If I gave you that 100 numbers, couldn't you go into the calculator and find the standard deviation of them? All I'm doing here is telling you what the answer is to save you the effort. Now, over in Washington's, you managed to find 200 places. And there was only 12 inches of rain in July, which is actually a lot. And that the standard deviation was, say, 2. So we've got our two populations, right? One is rain in July in Alaska, the other is rain in July in Washington, right? And we're going to find, right, an estimate for the difference in means. We are not going to do this by hand. Will you just trust me that if you try to do this by hand, we'd spend half an hour because it's just horrendously difficult to do, right? So we are only going to do these kinds of questions. So that's the one where the difference of means where sigma is unknown, right? We're going to do these questions on a calculator. Now I'm going to hit start. I'm going to hit tests. This menu, the test one, isn't it get kind of full up? Right, we're using it all over the place. I'm now going to scroll down to 0. It's called 2-sample T interval. You know that we've been using 2-sample Z interval? That was what we were using previously. Do you know that we're using 2-sample T interval now? So I guess I should write that down. 2-sample T interval. So I'm going to hit enter. And it's going to ask me for data or stats. I'm going to move over to stats. I'm going to hit enter. Now can you see that it has data from somewhere else, so we're just going to ignore that data. And I'm going to go and retype X bar, which is 15. The standard deviation was 3, and the sample size was 100. Right, you're happy about where those three numbers came from, right? They came from here. And then I'm going to do it for the second guys, right? These guys over here. I just realized I'm being inconsistent. Right? 1, 1, 1, 2, 2, 2. So let's do it for the second one then. The mean is 12 inches. And the standard deviation was a nice number. It was 2. And the sample was 200. I forgot again. What kind of confidence interval do you want to get this time?
$75.
Well, okay. So we'll pretend that, well, we won't pretend. If you were doing this question, they will tell you, right? They have to. So we're going to be 0.95. And then they come up with a question that you weren't expecting. You were probably expecting calculate. Agreed? So let me tell you what pooled and not pooled means. See if you somehow know that the standard deviation of the populations is the same number. You might not know what that number is, because you won't. But somehow or other, you might know it's the same number. If the answer is yes, it's the same number, you highlight pooled yes. The most likely answer, unless there's some other strong evidence to suggest it, you should really pick no. Would you agree that in most practical situations, you do not know what sigma is? So the chances are that you don't know what sigma is, but somehow you know whatever it is, both groups have the same sigma. Isn't that pretty much ain't going to happen unless they tell you, right? So just pick no unless they tell you in the story, oh, by the way, the sigmas are the same, right? If they just flatly tell you, then you pick yes. But if they don't, I would suggest strongly that you do know. Now I can hit calculate. Have you noticed that it took the calculator a fair amount of time before the answer came up? Can you imagine how many weird calculations it was probably doing? And can you also imagine why you do not want to do them? Right. So here we go. I am looking at an interval round about 2.3, let's just call it 2.3, up to 3.7. So the difference in Alaska to Washington is somewhere between 2.3 inches of rain to 3.7. Is that evidence that Alaska has more rain on average than Washington? Yeah. How do you know? Because the interval is all positives, right? So you can imagine there's a bit at the end of this where they say, what does this tell you? And one of them is Alaska rains more than Washington. The second one is Washington has more rain than Alaska. And the third one is you can't tell who's got most rain or whatever. Now we're talking about the average, right? Can you imagine there's a couple of places in Washington that might be really wet and a couple of places in Alaska that might be really dry. But we're talking about on average, Alaska has more rain than Washington, at least according to my data. Okay. If you wanted to put a number on it, wouldn't you say that it probably has about 2 inches more on average? You could say 2.3, but nice round numbers are better, aren't they? About 2 inches would do. Can we just pretend for a minute that I did a different set of data and my interval looked like that? Some negatives and some positives, right? Because all we've seen so far is everybody is positive and everybody is negative. And that's good intervals. We like those intervals because they tell us one group's bigger or less than the other group. But you can imagine there are going to be a fair chunk of times where the interval is both negative numbers in it and positives. When that happens, do you know that means there is no real evidence to prove that one of them is bigger or less than the other? Because if it was this number, it meant it was less, but if it was this number, it meant it was bigger, right? And isn't each number just as likely as any other? So you can't really separate out the chances. Does that look good? Right. Now, I'm going to give you one of these number ones to do. We'll see how that goes. So, Group A and Group B. And Group A is going to be Scottish people. And Group B is going to be Irish people. And it's going to be males. And we did a sample of 100 Scottish people who regularly go to pubs. And we went and asked them, on average, how much do you spend on drink in one visit to the pub, right? And the Scottish guys spent on average $20, right? Make it dollars. And the standard deviation was $5. The Irish people, on the other hand, we got 200 of them, and they on average spent $30, and the standard deviation for them was 10. And we're being asked to find a 99% confidence interval. Okay, you've got 3 minutes. Start hitting buttons on a calculator. Make that happen. Last few seconds. I mean, if you know what you do, it doesn't take long, right? If you know where the menus are. Let's see what we have here. Clear that out of the way. So I'll go start, I'll go over to tests, and I'll scroll down. Menu 0, enter. Would you agree we're still on the stats choice? So it's just a matter of putting in the data. In this case, Scottish people, $20 in one visit, 5 and 100. The Irish, $30, 10, 200. Well, that was coincidence. The level that we decided on, or I decided on, was 99. Do you think this is pulled, yes or no? Because if you pick one, you'll get a different answer. And I would strongly suggest that, excuse me, that you choose no. Now, one of my students said something that was quite interesting, and I think it makes sense to me. I'm not sure it's provable. But if you look at the two sample standard deviations, would you agree that they're not that close to each other? Wouldn't that probably mean that they're not equal in the population either then? That kind of sort of makes sense. And it kind of sort of made sense to me. If both of them were, 4.8 each, then I might be tempted to think maybe they are equal, in which case I do pulled. But scroll down to the bottom, hit a calc, and negative 12.25. And negative 0.7 I guess if I round it off, is 7.6. Okay, that's your interval. Here's one of these little things they tag on at the end. I couldn't think of a good one for the last one, so I just put in some nonsense. Based on this interval, can you say that Scots on average drink more on average than the Irish? Scots drink less on average than the Irish? Or you can't tell who drinks more on average? Or that depends if you're Scottish or Irish, how you answer that question. Okay, all those numbers are negative, aren't they? And if you're negative, doesn't that mean the first thing is less than the second thing? And the first thing is Scots drinking, and the second thing is Irish drinking. So doesn't that mean there is evidence here that Scots people, so you pick that one, right? Drink on average less than Irish. And I think it comes out in the data, don't they spend 20 and these spend 30? So it's pretty clear that that's at least the direction that the evidence is pointing. So do you feel comfortable about this question as far as it goes? Now, there's another flavour of that same question, which I'll just do as a kind of last version of that, and then we can move on to the last topic. Let's suppose you have your two groups, I like calling them A and B, and we'll have this as Class A and this is Class B. And in Class A, you just took a sample of the ages of 5 of the students, right? So it's one of those big university classes where there could be 200 people in it. And this is lecture room A, and these are the ages of the people. And over here is a different one. And just to keep my life easy, that's 5 people from that group as well. Now, in this case, the sample size is 5 in both cases. And I'll assume that there's no reason in the world that sigmas are equal, so we'll do the non-pooled one. And I would like a 90% confidence interval of the difference in means. So you want to do that. What you basically need to do is you use a calculator. We're pretty much have already done things just like it. Now, oops, I almost forgot. Don't you have to put the data in? This time at least I remembered. So I'm going to clear out the data from L1 and L2 because that's the default places where you put your data. And for the first one, we're going to put 15, 17, 23, 41, and finally 51. And then if I move over to the second place, I'll put in 22, 23, 27, 29, and 30. Gut feeling. Do you think that the first class, lecture room A, has on average older students than B? Or on average younger students than B? Or you think you're probably not going to be able to tell the difference, right? There might be, it might not be. Any gut feelings? Who do you think's the biggest, maybe? Who do you think's the oldest on average? A or B, or you can't tell? I'll put you in a spot. Madison, guess.
I'd probably say A.
Because of the 41 and the 51?
Yeah.
Yeah, that's kind of my gut feeling. I've had lots of gut feelings and then I get proved wrong. So don't worry if we get proved wrong. What you have to do in statistics is you might have a hope or a wish for a certain thing to happen, but see if the data comes back and tells you, and sometimes it does, it tells you the exact opposite of what you were hoping to be true. You're not allowed to just say, well, I don't like that one, I'm not going to publish it, because that's really not the way scientists should work. Shouldn't you publish whatever the data tells you, right? So believe the data, right? If the data tells you something. I'd probably qualify this. Would you agree 5 is a horrible sample size? But if I did it with 500 people, right, and it was a different story, you have to believe it, right? The data tells you that. If you don't like it, hard luck, that's life. Now I'll go over to tests, and I'm going to zoom down here. And we already know this guy. Isn't he 0? Because you don't know sigma, right? 0, hit it. Do you see I'm now going to move over to the data one and hit that. And it's saying list 1, that's where it is. List 2, right, that's where the second class is. 1, 1. 90% confidence interval. And then I say, no, the data's not pulled, right? I told you that right up front. So we should be able to come up with an interval and we'll see whether or not both of us have an agreement on this answer. And negative 11.9 to positive 18.3. We're just wrong. Well, let's rephrase it. Isn't it negative and positive numbers? Doesn't that mean we can't really tell if the difference is big or small? Right? You just can't. And I think I know why. Isn't that sample size of 5 killing me? So don't expect good results. Oh, and for a freebie, do you see all the other numbers that they give you? The mean of the first sample, the mean of the second? Okay, it's 3 years older, right? So the first class has an average of 3 years more than the other one. Standard deviations is what it is. What did I just do there? I keep hitting things I don't mean to hit, right? So you get lots of all sorts of good stuff, right? But the interval at the top's the important one. And that's the one you're going to base most of your conclusions on. So I am going to risk going out of this window, not losing anybody, loading up the homework, and we'll have a look at some of the homework. We'll only be able to do like the top 2/3, because there's one topic we still haven't done, which is number 3, and that's us finished when we do that. So fingers crossed nothing blows up, disappears, or any of that good stuff. Okay, looks like we're good to go. I think it's this one. Oh, come on. Urgh. Are you looking at the homework from wherever it is, 7-4? Oh, good. So I did get it right. I thought I'd lost it. Homework from 7-4, estimating differences. The first couple of questions are really to do with, you know, the bigger or less than. So in this question here, can you see that's like group A, you type them into L1, and that's going to be group B when you type that into L2. There should be a confidence interval somewhere floating around here. Did they give us a number and I just can't find it? Oh, shooting space. Do you see it's an 80%er? My self-control is amazing. I could have done a lot worse than that. Oh, by the way, see when you do this question A and B, since we're doing it with the calculator, do you know it's a good, oh, you can see the answers, but you know it's a good idea to do the calculator because it tells you these two, and as a kind of extra added, it tells you these 4. Do you know that's less work than just finding them out separately, you know, the usual boring, you know, one at a time way. So use your calculator and find the interval, and then underneath the interval, remember it had x1 bar, x2 bar, s1x, s2x. That's what these 4 guys here are. And I'm going to get rid of those answers because they're distracting me. Why can't I get rid of the answers? Okay, I'm not going to risk going back out and in again. The questions change anyway, so there's no guarantee that your answers are going to be the same. There's going to be a lot of same old, same old. Can you imagine that this question is virtually identical to the one we did? That's going to be data 1, that's going to be data 2. And then you go and you do your third. There's another one, that's third one like that. There's a 4th one. That's still to be done. That's still to be done. That's still to be done. Okay. This question 11. Do you notice that they've told you sigma? Right. See sigma 1 and sigma 2? You see that? Doesn't that mean that you're going to have to do difference of means sigma known? So isn't that going to be 2 interval Z thing, not 2 interval T thing, right? So there's one example of that. Can you now see, no, not that one. No, that's still to come. The usual data in. Okay, that's pretty much the end of the stuff now. Okay, so it looks like the homework is consisting almost entirely of the T interval one, right? The ones we just finished doing a minute ago, and the more laborious version where you have to type in L1 and L2 to get your answer, right? I think there's one example where sigma was known, right? I can't remember the question, but we saw it for a moment, right? So there's going to be one double Z interval. So who is left? Well, let's show you the guy. We're going to look at difference in proportions between 2 groups. Difference in proportions. So suppose I have 2 groups. It looks very similar to the start. 2 groups. In this case, we're going to have females. And in this group, let's say females older than or equal to 20. And the second group is females, I don't know, 15 to 19-year-olds. So teenagers, essentially, right? Just so that you don't get the thing that groups have to be males and females, right? Can't groups be anything you like? So we went and asked Group A, females older than 20. What should we ask them? Do you like very sweet chocolate? Can't think of where that question came from, but it came in my head, right? Do you like very sweet chocolate? And you asked 100 of these females, do you like very sweet chocolate? And P hat is how many of them said yes. And so let's say that 52 of them out of 100 said yes. So we'll call that N1, we'll call that P1, which as a decimal is 0.52. So far, so good. Then you went and you asked the 15 to 19-year-old, and you found 150 of those. And out of that 150, 90 of them said they liked very sweet chocolate. And so you would go 90 divided by 150. You think I could do that in my head by now? But I can't, right? It's 0.6. We would like to know if there's a difference in preference about sweet chocolate, whether both the groups are about the same, or do one group likes sweet chocolate more or less than the other. Now, rudimentarily, just looking at the data, if there is going to be anything, won't it be younger teenagers like sweet chocolate more than the older females, if this data was real, right? So you can imagine that we're going to have to create a formula, you would expect at least, for an estimate of the difference in proportions. And you might think that we're going to do some number examples by hand and then show you how to do it in a calculator. Does that seem reasonable? But I'm not. I'm only going to show you how to do it in calculator. And if you look up the textbook and you look at the formula that you use, you'll probably realize why. In the same way, you know the t-distribution stuff, we just basically let the calculator do it. Some things are just better done with a calculator. Go way back to the beginning. Didn't we never even try and get a standard deviation by hand? Remember how horrendously hard it would have been? I think I glanced over it. But if you look at the textbook, it's ridiculously difficult to do it by hand. Isn't it just much easier to get the calculator to do it? Because what we're going to spend our time on is in interpretation. So, here goes. Oh, we'll do the usual guess. What button do you think I'm going to hit first to get a difference in proportions? Come on, you know you want to tell me. What is it?
Start.
It is. Did you think it was going to be a trick question? Then I would say, you think it is, but it's not. Is that what you were worried about? I guess sometimes I do that, but not this time. Okay, so I'm going to hit start. Would you agree, because I don't want to spend 5 minutes waiting for you to finally tell me the answer, would you agree that it's probably going to be in the test menu? Doesn't that mean there's yet one more thing in that heavily used menu that you have to make sure you know which one does which job? And it might be a good idea to write a little cheat sheet and say, for this kind of question, use this one. for this kind of question, use that one, right? Do a little hit list, because there's about 5 variations now, isn't there? There's about 5 different things going on in there, and you need the right one. So I'm going to zoom by these guys. So far, so good. Now, do you know we're looking for an interval, aren't we? So that might be a clue in who we're going to use. But aren't we looking for a proportion interval? Can you see number 8, 2 proportion Z interval? I should say number B, whatever you want to call it. It's not an 8. And it's 2 proportion Z interval. Just to show you something that might seem a bit strange. Do you know that there's no 2 proportion T interval? Have you noticed they go in pairs? A Z guy and a T guy, a Z guy and a T guy, a Z guy, all the way through, except for these. Strange that, isn't it? That there isn't a Z or a 1 proportion T interval, right? But there isn't. So it's number or letter B, enter. Oh, surprisingly easy menu. Do you notice that this menu doesn't have L1s and L2s in it? Because when you do proportions, isn't the data pretty much how many people said yes? It's not like you had to write down 100 yeses and add them up or anything, right? So in X1, 52 people said yes out of a sample of 100. And then on the other side, X2, which is basically here, you get 90 people, the younger teenagers, out of 150. And did I forget? I did. Can we do a 90% confidence interval, right? Let's say that. That had to be part of the question. So I've already got it set up. About to hit calculate, go. And the number that I got here is negative 0.19 and positive 0.03. So our estimate for the difference between older females and teenagers is either negative 19% all the way up to positive 3%. Doesn't that mean that based on this set of data, you can't really tell for sure one way or the other? Does one group prefer sweet chocolate more than the other? So it's a kind of non-result. Now here's a problem, because they very often ask you, what's the margin of error going to be? Or if not, tell me how I'm going to get it. Maybe that's a better question. You'll have to hit spacebar, Kerry. I can't hear you.
We're going to add the 2 and then divide by 2.
Is it add the 2 or subtract the 2?
I guess it would be subtract.
Yeah, it's going to be subtract, but it's going to look like add. That sounds a bit strange, but here goes. Big guy, take away little guy. I'll show you on the calculator. Clear this out of the way. The big number is 0.03, right? It's positive. Subtract a bracket, negative 0.19. Do you notice that subtracting a negative is like adding it? So the difference between those two is 0.22. You then divide it by 2 and you get a margin of error of that guy. So that makes it 11%, the margin of error. Which is a pretty big margin of error, isn't it? Give or take 11%. Surprisingly big. I would have expected smaller, but I'm continually surprised by that. I guess in this case, 100 and another 150 just wasn't good enough, right? There's just too much going on. And so the margin of error was quite big. I'm pretty sure if that was 1,000 and this was 1,500, that would shrink down a lot. Right? So differences between two groups tend to have quite large margins of error, because can you imagine one mean might go this way and the other mean might go that way, and they're kind of pulling each other apart? And if you do that, you're going to cause a lot more variation. And in a way, isn't the margin of error just measuring the variation in your answer? In this case, the difference. So big.